Hi and welcome to yet another chemistry lesson, and in this one we're still looking at chemical energy changes, and specifically today or in this lesson I am looking at the Maxwell-Boltzmann energy diagrams. It sounds incredibly intense, and I suppose it's actually not that straightforward, but hopefully I can explain it in a way that will make sense to you. Okay, so basically what it comes down to is we are going to look at a diagram where on the one side we will have the energy levels of particles, so the kinetic energy of particles. Okay, particles, and here would be the probability of observing forgot my V, that kinetic energy. Okay, so before I'm going to show you the actual Maxwell-Boltzmann diagrams, let me explain it like this. Imagine we had intervals on here. Okay, so don't worry so much about what units. We're not looking at the actual values of these, rather just the shape of these diagrams. Okay, and so what we're going to draw first is called a histogram. So if you have some recollection of statistics, it's a statistical diagram, and what a histogram is, it looks at the frequency in that you observe a certain observation in a certain interval. So for example, what we will look at is we will go and see if we can measure the energy of particles. So here, and let me just make this slightly more colorful. Okay, here we have a container with particles in this container. Okay, so obviously I'm just explaining this as it is in my own mind. I'm not trying to be technically correct. But what we're going to try and do is measure, we're going to look at every particle's energy. Okay, and we're going to put that particle in the correct interval based on its energy. So for example, we notice that that particle is in this energy level, that particle is in that energy level, that particle is also there. Wow, this energy level has a lot. Okay, this particle, oh, he goes there, that particle, he goes there, another particle, whoa, another one in that energy level, another one here. This one, oh, is slightly small, and so we'll go on and plot our energy levels, or every atom in its energy level or particle in its energy level, and eventually what we will find is a histogram that looks something like this. Okay, something like this. Okay, so I'm not 100% sure how it will look like. Okay, but let's just look at the shape. The shape is what's important in the end. Okay, it will in fact make a shape like that. But now, if I were to decrease the size of this interval so that I can have a more accurate, so instead of having a wide interval like that, I just decrease the interval, then I'll see it might look like this. Let's change the color to illustrate. It might look, rather than this, it might look like this. Okay, like that. Okay, so I'm halving these intervals and seeing this is what I'm getting, something like this. Again, I'm not trying to be technically correct. I'm just trying to give you more or less the idea behind these things. Okay, so in the end we have something like this. As I'm decreasing my interval size, I'm getting, if I connected the centers of the original one, I did in orange, yellow, let's go. The centers of the original one is connected with these straight lines. Now when I connect the center, okay, I've got these shorter straight lines. And if I were to continue to do this, and in decreasing the interval, at some point I'll be looking at specific values. Okay, I would never really get there, but that's the intention, is decreasing these intervals until I get to a specific value. In that case, what I will have is, instead of these lines, if my bars in the end are actually smooth lines right next to each other, so I'm actually coloring in this whole thing so that the top of my curve is actually, well, the top of my diagram is actually a curve. I end up having a whole area because I'm looking at each value, okay? And in the end, instead of measuring anymore how frequently it occurs, I'm looking at the probability that it would occur at that value. This is called the probability curve, okay? And it's a smooth curve, okay? And asking the likelihood, what is the likelihood of observing a specific value? Now, when this horizontal axis is actually a continuous variable. Now I'm getting into the maths. I don't want to go there, but when it's a continuous variable, in other words, I can have as many commas as you can imagine, then the likelihood of observing a specific value, okay, thinking, well, what's the likelihood of observing an energy level of, let's say, I don't even know, 3. I don't even want to give it units. What's the likelihood of observing a 3? Well, that means you must find the energy level of a particle that's exactly 3, okay? Even if with no rounding, 3,0000000 forever. The likelihood of observing that specific value is probably 0. Okay, what's the chances of actually getting that specific value? So in a probability curve, it is not so meaningful to ask what's the likelihood of observing a value. What is more meaningful is to ask the question, what's the probability of observing a value in an interval? Okay, so for example, what's the probability of observing a value between these two values? And in a probability curve, that probability is the area that is covered under the graph for that interval. Now, when it comes to the actual maths, it ends up getting very complicated because there's complicated maths to actually go and figure this out. That's far beyond the scope of this course. But what I do want to use is I want to use this idea to explain to you how the Maxwell-Boltzmann energy diagrams can be used to explain how different factors affect the rate of a reaction. Okay, so I've been talking about energy levels here. Why am I talking about the rate of a reaction? Well, remember, the rate of the reaction, so rate of reaction is directly proportional to the kinetic, well, let's say the average kinetic energy of particles. If I can increase the average kinetic energy, which means on average all of the particles are moving faster, there's a higher likelihood of them colliding with one another with enough energy to start sharing electrons and breaking bonds. Okay, so that's the whole point. So let me explain then the Maxwell-Boltzmann curve when it is directly related to, or when it has exactly this on the horizontal and that on the vertical axis. So let me draw that again for you. Okay, so here again we have my best attempt at Maxwell-Boltzmann energy diagram. Okay, excuse my acronym, but this is my best attempt at it. And again, what it represents is the probability of observing a certain energy level in particles. So the kinetic energy level of particles. Okay, particles. Now you'll notice here this turning point here, this maximum that it reaches, this in statistics is the observation that occurs the most. Okay, so this value, whatever that value, that energy level is here, this is kinetic energy, that is called the modal. The mode is the most observed observation. The modal energy, the modal kinetic energy, okay, kinetic energy. Now, you might not a single particle might have that exact energy level, but what it means is that around this energy level, if I look at an interval around it, most of the particles will fall in this interval near and around the modal kinetic energy. Okay, so let's do the modal kinetic energy level. Is then here. Now the average kinetic energy is a little bit skewed. We call it skewed in statistics. Okay, it's skewed because if I work out the average, I'm literally taking the kinetic energy of one plus the kinetic energy of another plus the kinetic until I get to the kinetic energy of the last one, and then I'm dividing it by all of them. That would literally be the average. Now when I divide the total, the sum of all the kinetic energy with the number of observations or particles in this case, I will notice how these particles that have very high energy levels cause the average to be skewed. Okay, so on average it would be more than the modal kinetic energy. So let's make the average in green. Okay, so this might be my, actually that's a little bit far. Okay, that might be my average kinetic energy. Okay, now what we want, the desire for us before a reaction can occur, is we need particles to have enough energy to have successful collisions. So it's all about successful collisions. This is what it's all about. Now, which particles will have enough energy? Okay, it will be particles that fall above a certain level. So all the particles that fall, these will be the particles that have enough. Remember, the higher I go on here, the more energy it has. So all the particles that fall in this area here has enough energy to have successful collisions. And this energy level is called the activation energy. The activation energy. Okay, so you'll remember activation energy is the energy that we need to add in order for particles to reach the accelerated complex. That is the point at which it has enough energy for successful collisions. Okay, so at that point, this energy level is the activation energy, and that is what we want to reach. Now, based on this diagram, I want to show you what will the effects of be of changing aspects like temperature, adding a catalyst, etc., etc. Now, just so that this video doesn't get too long, I'll do all of that in the next video. So in the next video, I'll use the Maxwell-Boltzmann distribution diagrams or probability diagrams to illustrate the effects of factors that affect the reaction rate. Okay, we'll see you there.